Welcome to AI Paper Podcasts. Today we're diving into a really important one called Measuring Agents in Production, or MAP.
It's a huge deal because it's the first real large-scale study of AI agents that are actually out there, in the wild, not just in a lab.
Exactly, and it looks at them across 26 different domains. So what's the big takeaway? Well, the core insight is that success right now is all about simplicity and control.
They're not these all-powerful autonomous beings. They're very manageable.
Totally. 70% of them are just using off-the-shelf models, no complex fine-tuning, just prompt engineering. And this is the kicker. 68% run for 10 steps or less before a human has to step in.
Right, which all points to the single biggest challenge they found, reliability.
Which is why 74% of teams are relying on humans in the loop for evaluation. And one last thing, they're choosing quality over speed. Get this. 66% of these systems can take minutes to respond.
Which sounds crazy, but it makes sense when you see they're still way faster than the human they're helping.
That perfectly sets the stage. It's a real dose of engineering reality, showing that the best deployments were all about pragmatic, careful constraints.
Not just letting the agent run free.
Exactly. So, okay, let's start with the big question. Why are companies even doing this? What's driving them to adopt agents over, say, just building normal software?
It really boils down to efficiency and economics. The data is super clear on this.
It's about saving money.
It's about saving human effort, which is money. The top three reasons were, 1, increasing productivity, that was almost 73%. 2, reducing human task hours at 63%. And 3, automating routine stuff, which was half of them.
So pure and simple return on investment. You justify the cost of the model by saving time for your expensive human experts.
That's the formula. And you can see it in what they don't prioritize. The fuzzy stuff, the harder to measure goals are way down the list.
Like what?
Things like risk mitigation, that was only 12%. Or speeding up how you respond to failures, only 18%. If you can't put a clear dollar figure on the time saved, it's just not the main driver for adoption.
That pragmatism really shows up in just how many different places these agents are being used. I mean, we always hear about coding agents, but this study found them in 26 different domains.
Right. And the biggest ones were in finance and banking, almost 40% of them. Then you have technology and corporate services.
What does that tell you?
It suggests that the underlying pattern, this idea of bounded controlled automation, it works almost anywhere. You don't need a specific kind of problem. You just need a well-defined human process that's valuable but slow.
And the people using them are key to that control. Over 92% of these agents are serving human users, mostly internal employees.
Yes, that internal focus is critical. This isn't about replacing departments. It's about augmentation.
A tool.
A very smart tool for an expert, like a nurse or a site reliability engineer. That close relationship is what allows for the human supervision and, the verification that's so important for making sure it's reliable.
Which brings us back to that wild stat about speed. I mean, 66% of these systems are allowed to take minutes to respond. To an ML engineer, that sounds completely broken. Why is that okay?
This is maybe the most important trade-off in the whole paper. It's because these agents are doing tasks that take humans hours, sometimes an entire day.
Okay, give me an example.
Imagine a site reliability engineer who has to diagnose an outage. They're digging through logs, checking different databases, trying to piece together a plan. That could take 4 or 5 hours of intense work?
Right. Yeah.
So if an agent can do that whole process and it takes 5 minutes?
A 5-minute wait is nothing.
It's a massive speed up. We're talking orders of magnitude faster. So in that context, you absolutely prioritize getting the highest quality answer because the task itself is just inherently slow for a person. Latency is almost irrelevant.
The only time it would matter is if you're trying to have a real-time conversation with it, like a voice assistant.
Exactly. For those interactive apps, latency is a killer. But for deep analysis, capability is king.
Okay, let's pivot then. Let's look at how teams are building these things. If capability is king, what does that mean for their choice of models and their architecture?
It means they're going straight to the top. They use the most powerful models they can get their hands on.
It's the frontier models.
Yep. 17 out of the 20 teams they studied in depth were using the big closed source ones.
Yeah.
Anthropic's Claude family, OpenAI's GPT family.
But why not cheaper open source models? Aren't they getting better?
They are, but it's that same economic calculation again. The cost of running a top-tier model is like a rounding error compared to the salary of the senior engineer or the doctor you're trying to help.
So the ROI is just better with the best model.
By a long shot.
Mm.
If it saves that person an extra hour a day, it pays for itself many times over. The only time teams really go for open source is if they have massive scale and cost becomes a real issue, or they have strict regulations about data.
And the architecture itself is also all about simplicity. You said 70% are just using prompt engineering. Why are they avoiding the heavier stuff, like fine-tuning or reinforcement learning?
It's all about control. SFT and RL, they change the model's actual weights.
Yeah.
That introduces a ton of complexity, huge training costs, and this non-determinism that's really hard to debug.
It becomes a black box.
A very unpredictable one. With prompt engineering, if something goes wrong in production, the team can just tweak the prompt and redeploy it in, like, minutes. You can't do that if you have to retrain a whole model for weeks.
So the human is still dictating the logic just through the prompt, and they're writing these prompts by hand, right? The study said 79% of teams do it manually.
Right. Very little automated prompt optimization, things like DSPy. That stuff is still mostly in the research phase.
And some of those manual prompts get pretty huge.
Oh, yeah. While most are pretty short, under 500 tokens, there's this long tail. More than 10% of agents are using prompts over 10,000 tokens.
Wow. What for?
For really complex tasks where you have to feed it a massive amount of context, like entire documents or long conversation histories.
You can't be running a 10,000 token prompt through a giant model every time, though. That must get expensive.
You're right. Which is why most of these agents are actually coordinating multiple models behind the scenes.
Yeah. Okay. So they route different tasks to different models.
Exactly. It's often for cost optimization. You send a simple formatting task to a small, cheap model, but the complex reasoning goes to the big one. It's also just for good operations, like if you need to migrate from one model provider to another.
Makes sense. Okay. Let's talk about the constraints. We said 68% take fewer than 10 steps. Nearly half take less than 4. That seems incredibly restrictive. Why bound them so tightly?
It's the number one strategy they have to manage reliability. It's that simple.
How so?
The more steps an agent takes, the more chances it has to fail. You get cascading errors, you get unpredictable behavior, and your costs and latency can just explode.
So by keeping it short and using a predefined static workflow, which 80% of them do, they're trading away that open-ended autonomy.
For predictability, for production-grade reliability, it's a calculated trade-off every single time.
One last thing on architecture. The whole framework debate. There's a really interesting split here. Frameworks like LangChain are popular in the broader survey, but in the deep dive case studies, 85% of teams built their own custom solution. Why the difference?
This is so important for any engineer listening. Frameworks are fantastic for getting a prototype up and running fast.
For hacking something together.
For sure. But when you move to production, teams find that a custom build just gives them more flexibility. They need to plug into their own company's infrastructure, handle weird edge cases, and this is a big one, avoid all the extra baggage and dependencies that come with a big framework.
So the framework is a tactical choice for speed, but the custom build is a strategic choice for production.
That's a perfect way to put it.
Okay, so that leads us right into the biggest challenge of all, reliability. The study says it's the #1 technical problem, and that creates huge headaches for evaluation.
It really does. Traditional software testing methods just don't work very well here. For example, over 60% of teams don't even compare their agent to a non-agentic baseline.
And 75% don't use formal benchmarks. Why skip benchmarks? That's like standard practice in ML.
Because the standard academic benchmarks are useless for these tasks. They're all super domain specific.
So you'd have to build your own.
And building your own is a nightmare. The paper mentions one team spent 6 months just to get a data set of 100 examples. It's incredibly time-consuming and expensive. Plus, the non-determinism of the agents breaks your standard CI/CD pipelines.
Your automated testing.
Yeah, regression testing becomes almost impossible. You can't guarantee the same input will produce the same output.
So if formal metrics are out, how on earth do they know if it's working?
This is where the human comes roaring back into the picture. It's an overwhelmingly human-driven process.
Human in the loop.
All the way. 74% rely on manual evaluation from experts or end users. And even though about half of teams use an LLM as a judge to help,
There's a catch.
a huge one.
Huh.
Every single team they interview that uses an LLM judge also has humans verifying its work. It's never fully automated.
That's fascinating. So what does that workflow actually look like?
Okay, so the agent produces an output. The LLM judge looks at it and gives it a confidence score.
Right.
If the score is low, it automatically gets sent to a human for review. But and this is the clever part, they also sample a small percentage of the high-confidence outputs, maybe 5%, and send those to a human, too.
Ah, so you're auditing the auditor.
Exactly. You have to make sure your LLM judge hasn't gone off the rails or gotten overconfident. It keeps the whole system aligned.
That's a great pattern. Okay, what about security? It seems like it's a secondary concern, which is weird since, 69% of them are handling confidential data?
It's manageable because security is sort of baked into that constrained design from the start.
Because they can't do much, the risk is lower.
Precisely. The attack surface is small. Teams do things like making the agent read-only. So an SRE agent can suggest a fix, but it can't actually execute it.
A human has to push the button.
Right. Or they deploy them in sandboxed environments. By limiting the agent's power, security becomes a much more contained, solvable problem.
So we've basically landed on this reliability paradox. Success in production today means actively restricting the agent, fewer steps, read-only access, internal users.
That completely changes the problem. It's not about controlling a complex running process anymore. It's about verifying a final output.
Which is a much easier problem to solve.
Way easier. And the big question for all the researchers out there is, how do we start to relax these constraints without everything falling apart?
That seems to point toward a need for new kinds of architecture. The way we break down tasks now, task, subtask to step, is based on how humans organize work.
It might not be the best way for an agent. The future research here is about finding new control flows that give the agent more freedom, but in a safe way. Like maybe you merge, generate, verify, and search into one single, highly reliable step.
And the evaluation has to get better, too. It can't just be about whether the final answer is correct. We need better tools for runtime monitoring and observability.
Especially for tasks where the feedback is slow. You don't find out you made a mistake until there's a financial problem or a customer complains weeks later.
So we need to start thinking more like traditional enterprise software. We need to aim for 5 nines of reliability for agents.
5 nines, yeah. 99.999% uptime. That's the gold standard, and we are nowhere near that for agentic systems yet. Getting there is a huge testing challenge.
And looking forward, the clearest sign of where this is all going is multimodal. Right now, 93% of agents are just dealing with text.
But when you ask the teams what they're planning to build next, it's all about non-text data. They want to integrate images, video, scientific data, you name it.
That's where the next wave of complexity is going to come from, and the next wave of opportunity.
Absolutely. This MAP paper is just an incredible snapshot of where we are right now.
Yeah.
We're getting real value by using the best models we have, but managing the risk with very clever, very human-centric constraints.
So to leave everyone with a final thought, if you're an ML engineer, a researcher, or just someone building in this space, here's the challenge. Maximizing value today means designing agents with very limited autonomy, with a human checking almost every critical step. So what fundamental breakthrough in reasoning, in testing, or in architecture do we need to achieve to finally, systematically relax those constraints and unleash the next generation of truly autonomous, highly reliable agents in production?